So I hope I am audible. Can anybody confirm? Yes, thank you. So what we'll do today is we'll talk about optimization. Okay. And specifically in optimization, we will talk about heuristics and metaheuristics. So I have been using these two terms since my first class. So we'll see what does this mean. Okay. And how does it helps us to solve decision problems. Okay, so this is the topics I wanted to cover today. Specifically, I'll show one example of a heuristic, and I'll show the different kinds of meta heuristics we have, and one or two examples of the various kinds of meta heuristics. Okay. So what is optimization? Optimization is actually a decision process in which we are trying to find out best or close to best solution among a bunch of solutions from a set of possible solutions based on defined criteria. So you will have one objective function and you are trying to either maximize or minimize. So if you are a maximization optimization problem, then you are trying to maximize this objective function by choosing some solutions from all the possible solutions, right? And there may be some solutions that are not possible. So we'll see what I mean when I say some solutions may not be feasible. So from this set of solutions, you have to choose only those solutions which are feasible and that maximizes the objective function if it is a maximization problem, or minimizes the objective function if it is a minimization problem. Okay. So optimization is just a decision process in which we are trying to find the best or close to best solution from a set of possible solutions based on some criteria, decision criteria. So this criteria and objective function is same. Okay. I have just used two different terms, but when I refer to them as criteria or objective function, I mean the same thing. This plays a crucial role in resource allocation, decision making, machine learning, engineering, finance, logistics, and etc. Okay. So we have seen search problems. So when we saw search problems over there, we were solving a decision problem and we solved it using state space search. Over here, we will see more ways to solve a search problem. And over there, we did not explicitly mention about objective function and constraints. Over here, we'll see some of those concepts. Okay. Some real world example. So a logistics company use optimization to minimize delivery times by selecting the best route for its fleet. So for example, if there is a these delivery companies which provide deliveries to you, so the delivery personnel packed the goods and they follow a route. So they can have different objectives. So some objectives can be they have to traverse all the routes. Second objective can be they have to traverse the route such that their time to complete all the deliveries is minimized. There can be multiple objectives as well. So he may follow a route that best suits his objective. Okay. So over here, this best route can have different objectives. So over here, it is saying minimize delivery time. There can be other objectives also. So for example, I was telling you that he has to he can be minimizing the distance. So the distance he is travel, he can be minimized. Okay. So the examples in the first class which we saw, that Chinese postman problem. So that was a optimization problem where the objective was to minimize the cost of traveling or the distance traveled by the person, such that so the constraint was that he has to travel all the routes. So that was a constraint. Okay. So optimization problem can be formulated as a pair S comma F, where S is the search space. I will let you know what a search space is, and F is the objective function. So search space. So when I say search space, it means all the solutions, all possible solutions. So search space is set of all possible solutions you have. So for example, if I'm talking about a traveling salesman problem. So let me define a traveling salesman problem first. Okay. I have defined in the previous class as well, but just to refresh again. So traveling salesman problem, it is a very popular problem and the abbreviation is TSP. So what this traveling salesman problem is about is that there is a salesperson, individual one salesperson, and he has n cities. And he wants to, so he has a home base and he wants to visit each city exactly once and come back to that base. So if this is the base, suppose I'm denoting it as 1 and there are n cities, he wants to travel all the cities, right? And he wants to come back to the base and he should visit each city exactly once. And there is an objective. What is the objective? He wants to minimize the distance he is traveling in this tour. So this is known as a tour, right? So this is one tour. There can be multiple tours as well. So if this is, so these are the cities, he can have this tour as well, right? So this is also one tour. So this way it is going. This is going this way. So there can be multiple tours and he is trying to minimize the distance he is traveling to make that tour. There can be other objectives as well. The other objective can be he's trying to minimize the time taken to cover all the cities and come back to the base. That can also be one objective. So it depends upon what objective you have. But if this is the structure of the problem, then it is known as a traveling salesman problem. Now, what is a search space? So over here, a complete solution is a one solution. So for example, if I label the cities, so A, B, C, D, E, F. So what is the tool he has? He has for this, it is A, B, C, D, E, F and A, right? So the last A I'll just remove because it is just repetition. So I'll say F. So this is one solution to this problem, right? A feasible solution. For this, it is A, B, C, D, E, F. For this, the solution is A, D, then E, C, F, B, right? So this is another solution. And what is a search space? All possible solutions to a problem is the set of all possible solutions is known as the search space. So for this 6 city problem, there are 6 factorial ways you can arrange this A, B, C, D, E, F. So there are 6 factorial solutions to this problem, right? Is that all right? Why 6 factorial? Uh, is this clear to you? Why 6 factorial ways, right? So there are 6 factorial ways you can arrange these 6 numbers, and therefore you have 6 factorial number of solutions to this problem. What is the objective function? So for each of these solutions, it will have a objective function. And when you extrapolate, or when you have the set of all possible objective functions, then you will label it as objective space. So one is search space. Search space is the all possible solutions, and one is objective space. So all possible objectives you can achieve is known as the objective space. Now, what is a global optimal solution? A solution which has the best possible objective function value. So if it is a minimization problem, the objective function it has is best among all possible. So what does this mean? It means S star is one solution whose objective function is less than equals to all S, all possible S in the search space. So this is what a global optimal is. Okay. I hope it is all right. Right. So we'll see a decision making process. So how do we make decisions? First, suppose you are in a company and you have been given a problem. So first step is to formulate the problem. That means you have to identify the problem, identify the constraints you have, identify the objectives you have, what things are influencing what. So you see, in real life, problems are not very clear. You have to define it very precisely. Those definitions, when you combine it, then it becomes formulation of the problem. So for example, if you are trying to minimize cost of production, so you have to take into account the various factors going into the cost. What are the constraints, like labor constraints, material constraints, all those things you have to uh, bring together in a table and then formulate the problem. Okay, so this is my problem, these are the constraints I have, and that is cost is being influenced by electricity, it is being influenced by the wages of the workers and all those things. When you write it, then it means then you have formulated the problem. What is modeling? Modeling is the simplification of this problem, and then you are simplifying it to a mathematical model. So over here in today's class, we will not see mathematical model. We will see that in the next class when we talk about linear programming in details. But if you remember in the first class, when we were talking about how to convert a real life problem to a graph, over there where we were modeling it to a network model, right? That was not a mathematical model, that was a network model. So that real life problem is translated to an abstract network model. Similarly, over here I have written it can be transformed into a mathematical model, and by doing so you may lose some details, right? By doing so you may lose some details. Nevertheless, whatever the objective was, that will be captured by this model. It has to. Also, it has to capture the constraints, right? So it may lose details, but the essence of the problem should remain. Okay. So that is what modeling is. Now when you have constructed a model, then you will have to solve that model and you will try to obtain a good solution. So this, I have written it in inverted commas. It means that it might not be the optimal solution, it might not be the global optimal solution, it may be a good enough solution for me. Okay. And then you have to give this solution to the decision maker. When this solution is given to the decision maker, he will implement the solution and he will see whether it is this solution which you have given to the decision maker, whether he is whether this problem which he had is being tackled or not. So it might happen when you are abstracting the model. So you had a real life problem, you made a mathematical model, solved it, and then you implemented the solution. When you implemented the solution, you saw that it is not actually capturing or it is not giving you satisfactory results. Then what you have to do is you have to go back and see whether your model was accurate or not, whether it was capturing everything. So for example, there was some uncertainty in demand and you did not include that uncertainty in the mathematical model and you gave the solution without accounting for the uncertainty in the model. And the decision maker, what he did is he implemented the solution and he saw that it is not capturing the essence of the problem. So he saw that there is some uncertainty which you have not incorporated in the model. So you have to come back and then remodel it again, incorporating that uncertainty or whatever it is, right? So this is coming back to the model. There can be other ways also. So suppose the model was accurate, but you solved it using a technique which did not give you a very good solution. So you might have to go back to this step, optimize step, and use some different approach to solve the same problem and then give him the new solution. And this iterates until the decision maker is satisfied. Okay, so this is how decision making is done. So you see, the person who is doing the step 2 and 3 is different from the person who is doing 1 and 4. Okay, so this 1 and 4 maybe so a person can be a manager, so he is giving you some problem, and 2 and 3 is some, suppose, an optimizer. So that person is trying to model that real life problem given by the manager and then giving the solution back to the manager. And when that manager is implementing, then he is seeing that there is some drawback to that solution, then he will come back to the optimizer and then there can be some back and forth. Okay, so this is how decision making is done. Okay, now we'll go back. So actually this slide is not perfectly placed, it should have come first and then this slide should have come. Nevertheless, so we were talking about search space and objective space. So I have given one diagram to specify what search space and objective space is. So you see, this is a two-dimensional search space. So there is x1 and x2. So any solution is represented by x1 comma x2. Okay, and over here this objective space is also a 2D space. So each solution will give you one point in the objective space, and you can have multiple solutions pointing to the same objective function as well. So there can be multiple solutions which have the same objective function. So for example, in this traveling salesman problem, you have two routes with the same tour length. So what is it? So you have two solutions and that has the same objective function value. So this is the search space and this is the objective space, and it is a mapping. So each solution in the search space is mapped to a objective function value in the objective space. Okay, so this is a 2D objective space. In the traveling salesman problem, we had a 1D um, objective space. You can make it 2D as well. So what can be a 2D objective space? So you see, this is a search solution. You can have two objectives. Objective one can be minimize distance. Objective two can be minimize time. So each solution can have two objective function values. One will be what is the distance this solution is representing or it has, and what is the time that solution is giving you. So you can have a two-dimensional objective function for this problem as well. And if that is the case, then this problem becomes a bi-objective problem. Okay. And solving a bi-objective problem is a bit more difficult than solving a single objective problem. It is intuitive, I guess. Okay. Right. So we'll move on to the methods of solving these problems. Any questions? Okay. So in today's, yes.
Please, previous slide. Yeah. In the search space and objective space, is it necessary that there has to be one-to-one mapping? Means solution A must result objective space, must result only one objective space. Means a particular solution A can result into two objective spaces.
No.
Can there be?
You are going against the definition of a function. A function cannot have two domains. Sorry, one domain and there is two range. So two values in the function cannot have, right? So what I mean by that is, for one x value you cannot have two y values. So that is against the definition of a function.
No,
so
this is not x and y. These are totally different spaces.
So when I write,
one x cannot have two y values. But
so when I write y is equals to f of x, right? So this is 1D, this is also 1D, right? So what is happening is I have a graph like this. So you see 2x can have the same y value. So this is 1x, this is y is equals to suppose 1. So this x is also giving 1, this x is also giving 1, right? x1 and x2. But you cannot have 1x giving two values. That is against the definition of a function.
1x giving?
So you cannot have a function like this. So 1x is giving you two y values. This is against the definition of a function.
Okay. Okay. Will you please show me the definition of function space, please? No, previous slide.
Which one?
Where the definitions were written, function space.
Okay, so this I have not written any definitions. These are just descriptions. If you want definitions, then I'll have to give you more resources. These are not definitions. So what I've written is what is search space, set of all possible solutions from a optimization problem. So these are just descriptions, not definitions. Huh? So what is an example for traveling salesman problem? The search space consists of all possible routes. So this solution A can be one route, solution B can be another route, solution C can be another route, and so on and so forth. What is an objective space? A space defined by the values of the objective function for all possible solutions. So if you have a solution here, it should have a solution in the objective function value in the objective space also. So it cannot have. So you will not have a.
If I read the objective space, the space defined by the values of the objective functions for all possible solution. It is never said that each objective space is defined by only one solution. And second, even in the second point, each point in the objective space corresponds to the evaluation of a point in a search space. So solution A can also correspond to f of a, solution B can also correspond to f of a.
Yes, that can happen.
It be true?
That can happen. Two solutions can give you the same objective function value. That can happen.
Yeah. That's what I mean to say. because you mapped here one to one, means solution A corresponding to f of b and solution B corresponding to, sorry, solution A corresponding to f of a, solution B corresponding to f of a. This may happen that solution A comma solution B corresponds to f of a.
Yes, so I gave you one example, right? So suppose these two are the solutions. So this is solution 1 and this is solution 2. Both can have the same distance in a traveling
Huh.
salesman. So that can happen. You can have,
Just needed to confirm. Okay. I
right?
thought there has to be, means solution A resulting only f of a and solution B resulting only f of a. That's not the case.
No, no,
Okay, okay.
right? So, but you cannot have one solution mapping to two different values in the objective space. You cannot have that. So
Okay.
what I mean to say is that two solutions can correspond to one objective function value, but you cannot have one solution corresponding to two different objective function value. You cannot have that. So this is not possible. Okay, right. Okay, right. So in this class, we will not talk about exact methods a lot. We will talk about exact methods in the next class, and we will also cover constraint satisfaction problem in the next class. Yes.
Because, sorry to interrupt you once again. Previous slide. No. So objective space and search space. So in this particular graph, shall we say that objective space is a dependent space and search space is an independent space? Shall I
Yes.
roughly define?
So I will write the
Okay, mean,
mathematical expression for these two. What is happening is, you see, function. So this is the, it is f of a. So this f of f is a two. So you have two objectives, right? Objective 1 and objective 2, right? So what is happening is, suppose f1 is objective 1. It is a function of, so I'll not write f because I'm using f as function. So suppose h1 is a function of x comma y. So this is x and this is y. Okay. And what you have another objective which is h2, which is a function. So this is f1 and f2, or I can write g. So g can be also a function g of x comma y. So you have a bi-objective problem. So first objective is h1, second objective is h2, and you have two dimension x comma y. So this is what is being shown in the previous graph. Okay.
okay.
Right. So what I'm saying is, we will not dive deep into exact methods today. We'll study this in the next class. Okay. But I have given a brief introduction of the exact methods. So what it does, it in exact method, you will obtain the global optimal solution. Okay. So obtains the global optimal solutions with a guarantee of optimality. So this optimality is guaranteed in exact methods. That is why it is known as exact method. Some examples can be dynamic programming, branch and bound, constraint programming, and A star families of algorithms. So if you go back in the state space search, when we were talking about adversarial search, we talked about A star family of algorithms like depth first search, breadth first search, and other A star algorithms which uses some helper functions. Those are all exact methods. You are guaranteed to find an optimal solution. Okay. Some applications. So whenever you have the restriction of finding the global optimal solution, you have to use an exact method. So that is an application. Okay. Right. So what is an approximate method? So whenever you have obtained a solution and you cannot guarantee optimality, then you are saying that it is an approximate solution to the problem, and we are using an approximate method. There are two different classes of approximate methods. One is approximation algorithms and other is heuristic algorithms. So what is approximation algorithms? You see, approximate and approximation, there is a difference in terms of this words. So you have to be careful. What is an approximation algorithm? Approximation algorithms will not guarantee you optimality, but it will offer you a bound of solution quality. So for example, if you have a minimization problem, okay? So you have a minimization problem, and suppose the suppose the optimal solution is 5. So we know from somewhere, we have done some exact methods also, the optimal solution is 5 and we have a minimization problem, right? So what this will say is it will give you one solution, any solution. So suppose x is a solution which gives the objective function value as 7 or something like that, any value. So this value will be bounded by this value. So what it will say is whatever this x is obtained by this approximation method will be no worse than twice the optimal solution. So what it says is, suppose f star is a optimal solution. So this f of x will always be less than equals to, suppose a times f star. So a is some number greater than 1. So suppose it is 2. So what it is saying is f of x will always be less than equals to 2 times f of f star. Therefore, if f star is 5, then you will never get a solution so you never get a solution more than 10. You will always guaranteed to get a solution less than equals to 10. So that is what an approximation algorithm is. It will not guarantee optimality. It may be that you have obtained the optimal solution, but you will not know. This class of algorithms gives you a solution which is not guaranteed to be optimal, but there is a bound, this kind of bounds. So your solution is at best, so at worst इतना हो सकता है, मतलब खराब से खराब केस में it is a times that objective function value. Okay, so I hope what approximation algorithm is, it is clear. So if 5 is the optimal solution, this approximation algorithm, if it is 2 approximation, so when I write a is equals to 2, it is 2 approximation. Okay, so it says that your solution will not have objective function value more than 10, never, using this approximation, 2 approximation algorithm. If you have epsilon approximation, this a will actually be epsilon. Okay, in that case, this a will be epsilon. So that is the worst possible solution you can obtain using this approximation algorithm. Okay, so this is what approximation algorithm is. Now we will talk about what is a heuristic algorithm. So heuristic algorithm is actually a algorithm which tends to give you good solution, but there is no guarantee, no bound, no guarantee, no bound. Matlab, it can be very worse, but in general, it gives you good enough solution. Matlab, you have to accept कि चलो मेरे को good enough solution मिल गया है, but I cannot guarantee कि 2 times worse होगा या 3 times worse होगा. No guarantees are given. Okay, that is what is known as heuristic algorithms. Best suited for large and complex problems where exact methods are infeasible. So in traveling salesman problem, so whenever we are talking about traveling salesman problem, it's a very difficult problem to solve, right? So when you have a large problem where the number of cities are very large, so you see if the number of cities are n, and if you do exhaustive search, you will have to do n factorial searches, right? So for each of the solution, you have to obtain its objective function value and then pick the best objective function value. So if you do a naive exhaustive search, then you have to do n factorial, and it grows very fast. You can just check in your computer that how fast it grows. So 15 factorial you can check, and then you can check 20 factorial, and then you can check 30 factorial. It grows very, very fast. Okay, so this is the worst possible complexity. I don't wanted to use this term, but it is the worst possible complexity of an algorithm. So this kind of factorial complexity algorithms. Okay, so we have talked about what a heuristic is, what a approximation algorithm is. So we will focus in today's class approximate algorithms. So approximate algorithm is a class of algorithms which contains heuristic algorithms as well as approximation algorithms. Okay, so exact versus approximate methods. So in exact methods guarantee global optimal solution. So if you use exact methods, you are guaranteed to obtain a global optimal solution. Examples can be branch and bound, constraint programming. I gave you some examples. Suitable for small problems due to computational cost. So when the problem size increases, okay, but one more thing I have not written here is that in some problems, exact methods, so some algorithms, so what I'm saying is, you see, although I have written that it is suitable for small size problems, some classes of problems are easy to solve using exact methods. Okay, so for example, shortest path problem. It has an algorithm which gives you optimal solution in polynomial time. So that is one caveat which I have not written here. Okay, so some class of problems are there which can be solved to optimality within polynomial times. Okay, so that is one thing you have to remember. Approximate algorithms provide near optimal solutions in reasonable time. Examples can be heuristics, meta-heuristics, approximation algorithms, and it is suitable for large and complex problems. And why I am giving you such kind of terms, some class of algorithms also. So if you study complexity analysis, then you will realize that there is classes of problems, and some classes of problems are easy to solve as compared to the other. So those I am not coming over here, but if some of you are interested, I can refer some sources where you can study those things. So I'll give you one example. So some classes of problems are in P class. So this is a class in complexity theory. What does it mean? That if any problem is in class P, then there exists an algorithm which can solve it use in polynomial time. So what is polynomial time? So n to the power, so n to the power x. So some polynomial function. Okay. So where n is the number of inputs to that problem. So in this traveling salesman problem, n is what? N is the number of city. Okay. So if you have a algorithm to solve this TSP in polynomial order, so n factorial is not polynomial. Okay. So suppose you have something like n to the power 8 or n to the power 7 or something like that, algorithms which can solve in these many steps. Then you have, so then you can say traveling salesman problem belongs to the class P, and it is not true, by the way. Nobody has proved if traveling salesman problem belongs to the class P or not. If it is so, so suppose somebody proves that traveling salesman problem belongs to the class P, then it will be a revolutionary result. And moreover, our encryption algorithms like banking password and all are using the concepts of that class, which is known as NP class. Okay, so this traveling salesman problem belongs to the class of NP, which are difficult. Actually, it belongs to NP hard, by the way. I'm not going into that, but it is very difficult to solve TSP in polynomial time. Okay, so that was a detour. I'm sorry for that. Okay, so we will see how we tackle problems using approximate methods. So first of all, you have to understand representation. So you see, for the traveling salesman problem, I told you that you can represent a solution using letters. So like A, B, C, D, E, and F. So if there are 6 cities, you can just write the expression like this: A, B, C, D, E, F, and we will say that this is a solution to that problem. So this is one representation of the one solution which I have represented it like this for a traveling salesman problem. Okay, so this representation is important. This representations is important when you use heuristics and meta heuristics. Why? Because you will try to manipulate this representation to manipulate to obtain good solutions. So this representation are um, key concepts for this kind of methods. So any solution, you have to try to represent it in some way such that you can manipulate that solution. So there can be binary representation. What is a binary representation? So to understand binary representation, we have to understand a problem known as the knapsack problem. So what is a knapsack problem? So suppose you have a knapsack. So what is a knapsack? Just a bag. So you have a bag and it has a capacity. So suppose we'll say that it can hold maximum W weight. So suppose W is equals to 19. So it could hold a weight of 19 kgs and not more. Okay. That is a knapsack with capacity 19. And there are some objects. So suppose a thief has entered into my home and he has a bag which can hold capacity of 19, and these objects has weights. So suppose this W1 is, so this is small w, W1 is 2 kgs, W2 is 7 kgs, and so on and so forth. Each object has some weights, and each object also has reward. So suppose this bottle, it may be sold in the second hand market for 100 rupees, something like that. So each has some weight and some reward. So this is the reward. So suppose R1 is equals to 7 units, some units, rupees or something like that. R2 is equals to 10 units. Now what this uh, thief want to do is he wants to store these objects in the bag such that the reward is maximized and does not exceed capacity. Okay. So the problem is He wants to put as many objects as possible in the bag in order to maximize the reward. He wants to maximize the reward such that the capacity of the bag is not exceeded. So what can be a representation of a solution? So you see, suppose there are n objects. So you create a list of n numbers. Okay, so these are n. So this list has n numbers. Okay, and each number corresponds to that object's label. So suppose this object is labeled 1, this object is labeled 2 and 3 and 4 and 5 and n. Okay, so each object is being labeled, and when this is 1, the first label is 1, it means the first object is picked. And if the label is 0, so over here second position is 0, it means that object is not picked. So 0 means the object is picked, 1 means the object is not picked. So what can be a solution to this problem? All 0. That is a solution to this problem. The objective function is 0, so you do not put any object in your bag. That can be a solution to this problem, right? So whenever you pick a solution, that becomes 1. Whenever you do not pick a solution, that becomes 0. Okay, so that is one representation of this problem, and that is known as a binary representation. Is that all right? A binary representation. So there are items, and for each item you have a value which can either be 0 or 1. Whenever it is 1, it means the object is selected, and whenever it is 0, then the object is not selected. Okay, is that all right? You can have other representation for the same problem as well. So what can be another representation? You just say the objects which are picked. So suppose what another representation can be. So you can have the labels as the representation. So when you have 1, 2 and 3, it means you are picking 1, 2 and 3. Whenever you have 3, 7, 5 and 7, so it means you are picking 3, 5 and 7. So these representations are important when you go ahead and use the algorithms which we'll talk about today, and which representation will help you is defined by the algorithm which you are using. So if this algorithm, this representation is more beneficial for you, or this representation is your decision to make. Whenever you are using an algorithm, you have to decide what representation will suit your purpose. Okay, so any representation you can write, but it should suit your algorithm which you're using ahead. So this is a binary representation. Another is a real valued representation. So generally in linear programming, so we can have, suppose for a factory there are two products, product 1 and product 2, and there are machines, so machine 1 and machine 2, and we are saying that product 1, machine 1 can produce product 1 at a cost of or not cost, in time 8 hours, and product 2 at 6 hours, and machine 2 can produce product 1 as 3 hours and this as 5 hours. Now the question is how much to produce these products, and the objective is like maximize the sales price, total revenue. So suppose 8 rupees is 800 rupees is incurred for each unit of product 1, and 500 rupees is revenue, is the revenue when producing product 2, and each machine can has limitations. So suppose machine 1 can be run for 8 hours, and machine 2 can be run for 16 hours, something like that, right? So the question is what should be the production quantity of these products, product 1 and product 2, such that the capacity of the machines are not exceeded and you are maximizing the revenue. So this is one problem I had just made in the fly. The thing I am telling you is that these products, so suppose think of it as some kind of lotion or something. It is in liters, so you can have 2.5 liters, 3 liters or something like that. So these are real valued numbers, right? So P1 and P2, so over here I have represented at X1 and X2, can take any real values. So those are also representations. So you are saying X1 is greater than equals to 0. It means it can take any value between 0 and infinity. So X belongs to, so this is equivalent to writing X belongs to 0 comma infinity, right? So this is one representation, real valued representation. Okay. Suitable for meta-heuristics like simulated annealing, particle swarm optimization. We will not go through these algorithms, right? We will only see basic algorithms and the most popular ones. So we'll not see particle swarm optimization. But I'm telling you this because if you find yourself solving such kind of problems, so you should know that these kind of representations are available and you can use these kind of representations to solve the problem using particle swarm optimization or something like that. Okay. Permutation representation. So for the traveling salesman problem, whenever we were writing a solution, we were saying we were representing it as a permutation of cities, right? So that is a permutation representation. So whenever you are trying to write a sequence, so suppose you have some jobs. So you have a machine one, and you have some jobs A, B, C, D, and E and F. Okay. Now what are you trying to do is you're trying to process all the jobs in the machine, and each job has some due date. So suppose A has due date of 10 days, B has due date of 7 days, and so on and so forth. And you're trying to meet those due dates. So in which order should you process these jobs in machine such that this is no job is delayed, something like that. So that representation can be a sequence, and that can be represented as permutation representation. So one solution is this, another solution is D, E, B, A, C, F, something like that, right? Any permutation is a solution to this problem. Any everything is all right, right? Understood, right? Any doubt? And you see, this kind of representations helps to ensure the constraint that each city is being visited once. You see, when you are writing a permutation representation for a traveling salesman problem, you are inherently putting the restriction in the representation. So in this representation, you will never have repeated cities. In the contrary, if you are using a binary representation for traveling salesman problem, so suppose there are 6 cities A, B, C, D, E, and F, and you're saying I'll represent it as binary. So suppose this is everything should be one, by the way. So this will not work because you have to visit all the city and you don't have a sequence. What is the sequence in binary representation? You don't know. So what you can do, I'll just go slowly. So what I'm saying is, for a binary representation, suppose I'm saying you have 6 cities A, B, C, D, E, F, and you have to visit each city. So you will have to put one in each of the city. Now you don't have a sequence. You're just saying in this representation, you're just saying pick all the cities. What does this mean for the traveling salesman problem? It means nothing. So what you can do is you can, instead of using the nodes or the cities, you can use the edges. So you can say AB is one edge, AC is one edge, AD is one edge, AE is one edge, AF is one edge, BA is one edge, and so on and so forth. And for each of the edges, you can have either 1 or 0, right? In this way, this can also be a representation of traveling salesman problem, but it has a serious limitation. So before the limitation, did you understand this representation? So what I'm doing is I am saying A, B, C, D, E, and F, right? A, B, C, D, E, and F. Now I am saying the edges. So there can be multiple edges, right? You can have edge like this, like this, like this, and so on and so forth. So I'm saying for each of the edge, it can either be 0 or 1. So when it is 1, you are going using that edge. When it is 0, you are not using that edge. So when I'm saying AB is equals to 1, it means I'm using this edge, right? Sorry. I'm using this edge. So I'm saying, so have you understood this representation, binary representation of this traveling salesman problem? Now there is a serious limitation in this representation. Can you find out the limitation? You see, you can, so in this representation, you may visit a city twice or thrice or more than once. So for example, you are picking this, and this. It can happen, right? So you are making AB as one, AD as one, and AE as one. Now you see, you are coming to A more than once. So, and also you can have multiple tours. So you may not visit every city in one cycle. So this representation lacks that limitation. You have to enforce the limitation in some other way. So suppose you are using this representation for some purpose, like your algorithm suits binary representation. You have an algorithm which works very well for binary representation, and you are forced to use binary representation. Then you have to ensure the constraint that each city should be visited once. So using this representation, you have to have some kind of constraint in the algorithm which prevents the invalid tours. Okay. So I'm not saying you cannot use this kind of representation. You can use, but you have to take care of that constraint somewhere else. On the contrary, using the permutation representation prevents that subtours or invalid tours, and it is inherent in the representation. Okay. So again, this slide should come in the tomorrow's class, but I have mentioned it here, some classical optimization methods. So over here, I'm talking about exact methods. Okay. Linear programming, integer programming, non-linear programming, mixed integer programming, constraint programming. These are all part of exact methods. And why I have mentioned is because these are known as classical optimization models. And today, which we will see is these methods have been developed in the past 2.5 decades. Okay. Later, so metaheuristics, the development of metaheuristics started in around 1970s, but the major chunk of the development was around 2000s. Okay. So that is why I am referring these methods as classical methods, because these were used, I guess, from the Second World War. Okay. So linear programming is one method in exact methods, and we will talk about this in the next class. So I'm just skipping it from here. Okay. So heuristic. So what is a heuristic? So you see, in approximate algorithms, we talked about heuristics and approximation algorithms. We will not talk about approximation algorithms. It will go into a lot of mathematics. In heuristics, we can have two kinds of. So one is a general heuristic, which is just known as heuristic, and one is meta heuristics. Okay. So I'll give you one example of a heuristics and 2-3 examples of meta heuristics. So what is a heuristic? Heuristic is problem specific strategy designed to give you good enough solution in less amount of time. Okay, I'll show you one example. So what is this? It is problem specific. So whenever there is some property in your problem and you can recognize that property, you can utilize those properties to build an algorithm. And whenever you build that and it is not an exact method, then it is known as a heuristic method. Okay, often based on domain knowledge and intuition. What is the advantage? It is simple and computationally efficient. It doesn't become non-polynomial. Okay. Effective for small, well-defined problems. Not generally, this is not exactly correct. It can be effective for large problems as well, provided you could find a good heuristic. Okay, so this line is not actually accurate. Okay. What are some examples? Greedy algorithms, rule-based algorithms for scheduling, routing, and so on. We will see this greedy algorithm, one example of that. Limitation, no guarantee to find global optimal solution. Meta heuristics also doesn't provide any guarantee. So heuristics will also not provide you any guarantee. Meta heuristics will also not provide you any guarantee. Can perform poorly for complex and complex problems. So you see, when we are talking about heuristics and meta heuristics, heuristics depends upon some problem specific characteristics. And if that problem is very complex, coming up with a heuristic to solve that problem becomes difficult. So that is why I have written it can perform poorly for complex problems. Okay. But meta heuristics are general purpose algorithms. So we'll go there. So what are meta heuristics? It is a general purpose framework for solving a wide range of optimization problems. You can solve almost, I'll not say all, but almost all problems using meta heuristics, provided it has that structure, and it will give you good enough solutions to work with. It will not provide you optimal guarantee of optimality, but it will provide you good enough solution to go ahead. Like when you find a route in this Google Maps, it uses some heuristics and meta heuristics to give you that route, and it is being done in real time, right? It is not taking 7-8 minutes to solve that problem. It is doing it in real time. So what it is happening, it is giving you good enough solutions to work with. You don't require the optimal solutions, right? You just need some route which is near optimal and good enough for you. So those kind of situations where you need solutions in real time or very short amount of time, in those kind of situations, these kind of algorithms are very useful. So we will talk about this exploration and exploitation in a little bit. Just give me a minute. What are some examples? Genetic algorithm, local search, simulated annealing, taboo search. These are some examples of meta heuristics. I'll show you what it is. Comparison with heuristics. Heuristics are simpler and fast, but less robust. Meta heuristics are slower. It can take more time than a heuristic. So meta heuristics can take more time, but can adapt to a very wide range of problems. Okay, so I've written some applications. So before coming to this exploration and exploitation, I will take you further and then I'll come back about talking about what is exploitation and what is exploration. First, an example of a heuristic. So we talked about knapsack problem. So what was a knapsack problem? You have a bag, it has some capacity. So over here that capacity is 15 units. It can be kgs, it can be volume cubic meter or something like that. And you have some objects. So over here I have 4 objects. Each object has weight and some utility, and the objective is to maximize the total utility without exceeding the capacity. So what is a greedy heuristic? It finds the ratio of utility to weight. It finds the ratio of utility to weight. So it is something like for each unit of weight, what is the utility you are getting? So for object 1, 0.6 is the this ratio. It means for each unit of weight, so suppose this is in kg, so object 1 is of 5 kgs. It means that for each kg you are getting a utility of 0.6. For object 2, so when you do 3 by 4 it becomes 0.75. So for each kg of object 2 you are getting a utility of 0.75. Similarly, for object 3, for each kg of object 3 you are getting a utility of 1.4, and for object 4 you are getting a utility of 0.67 for each kg of object 4. Okay, so this is the utility per kg when I am saying the weights are in kg. Okay, and now what greedy algorithm will do is it will pick that object with the most utility per unit of weight, right? Per weight. So it will pick object 3 first. So when it has picked object 3 first, it has got a utility of 7. So what is the utility? Capital U. It is 7. And what is the weight it has accumulated? It has accumulated a weight of 5. Now object 3 is gone. Now among object 1, object 2 and object 3, object 2 is more what you can say is lucrative. So object 2 is picked. So when object 2 is picked, the utility is 3. So you will add utility 3. So 7 plus 3. And the weight is now is 5 plus 4. So you have weight of 9. And the total capacity of the knapsack is 15. Now object 2 is gone. So among object 1 and object 4 seems more lucrative. So you can pick object 4. Sorry, utility will be added by 2. And the capacity is 3, so you will add 3. So currently you have 12 units of capacity you have used, and whatever the utility is. Now object 4 is gone. Object 1 you want to pick, but it has a weight of 5. If you add 5 it becomes 17, so you cannot pick object 3, sorry, object 1. So what this algorithm will do is it will pick object 2, 3 and 4. It will pick object 2, 3 and 4. It will not pick object 1. So this is how a greedy algorithm works. So this is a heuristic algorithm. And if you remember in some class I told you constructive heuristic. Constructive algorithms. RITH, right? So this is a constructive algorithm. It builds a solution one step at a time. So initially you had no objects picked, then it picked one solution, one object, then it picked another object, and at last it gives you this solution. So it is constructing the solution, therefore it is known as constructive algorithms. Okay, a constructive algorithm. So this greedy algorithm for a knapsack problem is a constructive algorithm. It does not guarantee optimality, although it gives you very close solution to optimality, but it doesn't guarantee optimality. Neither does it guarantee some approximation. So it doesn't guarantee anything. Okay, but it gives you good solutions. And this is a heuristic for solving a knapsack problem. And by the way, this knapsack problem is a very famous problem because it is applicable to many fields. So I have given you one example, but you can think applications of this problem in wide areas in real life, right? So I don't recall many examples, but if you go in the internet and check applications of knapsack problem, you will see endless results. Okay, so this traveling salesman problem, knapsack problem has endless applications. Any doubt?
Why is it called heuristic?
So over here we are getting a solution, but we are not saying that we cannot prove that this is an optimal solution.
So heuristic means we may get some solution, but does not have any proof. We shall call it as heuristic, or
No, I'll not say proof. The solution which it gives, that solution, it doesn't guarantee that it will be an optimal solution. So you can say it cannot be proved that it is an optimal solution, right? So you will not be able to say that this is optimal solution. That is what a
means
heuristic.
okay, we can consider like based on our understanding we are solving the problem, basic understanding, but uh, it may not be optimal.
No. So
Like
you
that.
see, heuristic is actually means the art of discovering new strategies. In plain English, this is what it means. Art of discovering new strategies to solve problems. So this is what heuristic means in English, and the word meta means upper level methodology. So the term meta heuristics in combined means some general class of methods which can give you solutions. It doesn't guarantee any optimality or something like that. Okay.
Okay.
So yeah, so I have given you the problem statement, the approach, and the limitation. It may overlook. So I'll give you one idea why this may not be an optimal solution. So you see, over here we are just picking one item at a time, right? So what is happening is when I have picked these three items, you see we have a weight remaining which is 3. So we have 15 minus 12, which is 3. And suppose there are more objects, and if you would have not picked what is this object, this object is object 2, no, this is 3, this is 2, and this is 4. So suppose you have not picked 4. If you have not picked 4 and there are some object, suppose object 6, which when combined with object 8, these two combined filled the capacity to 15. And suppose object 6 has a utility of suppose 2, and object 8 also has a utility of 2. So you see 5 plus 4 plus 4, you would have got a utility of, so I'm saying over here, so 7 plus 3 plus 4, it would have become 14. So you are actually just greedily picking objects. You're not looking at what may happen if you would have not picked one object now and waited for some other object in the next. So some combinations you are missing. You can think about combining two objects at a time. So what you can think is, over here you could have thought that, okay, over here I am looking one object at a time and obtaining the utility per weight. I can see two objects at a time. So what is the utility 1 plus utility 2 by W1 plus W2? This will also give you one factor. And this factor is what? Utility per unit weight of combined object 1 and 2. So these kind of things we are neglecting in these algorithms. And you see this can go on and on. You can have two objects combined, three objects combined, four objects combined, and you can have many more combinations of like this. So yeah, I guess I have made it clear, right? Okay. So this is what I have shown you. I guess this number I have not written correctly. So yeah, you can just check. I guess this is becoming 13. I don't know why I got 12, but yeah, so this may be incorrect, but the logic which I told you is correct. Okay. The greedy approach provides a feasible solution, but not guarantee the optimal one. Limitation: greedy approach does not consider combinations that might yield higher utility. Okay. Okay, so this is again I am writing the same thing. Limitations of greedy algorithm. The greedy approach focuses on local utility maximization because we are just picking the maximum utility per unit weight at the start. We are not looking what may happen in the future. So it doesn't have a look ahead factor. It is just a very short-sighted algorithm. It just looks whichever is the maximum and picks it. It doesn't consider the whole space at a time. Okay, so this is a very short-sighted algorithm, local algorithm, right? Limitations, I have told you, some examples I have given. Alternate approach: so if you want to solve a knapsack problem to optimality, you can use dynamic programming. And again, we have not talked about dynamic programming. I am thinking to cover it in the next class. Okay, so you could use dynamic programming to solve knapsack problem, and you will obtain a optimal solution, exactly optimal solution, if you let the dynamic programming run, terminate it. So you may, so what happens is you can stop an algorithm, exact algorithm at some point of time. Suppose you have an exact algorithm and it may take 3 days and you do not have that much amount of time. So you can terminate the exact algorithm in suppose 1 hour or 2 hours, and you may get a feasible solution. That solution will also not be an optimal solution. And in that case, you are using a heuristic. Although you are using an exact method, but you did not let the exact algorithm to run completely, and you are stopping it at some point of time. And you are saying whatever feasible solution it is giving me, I will work with that. Therefore, that algorithm is also a heuristic algorithm. Okay. So for this dynamic programming, you have to let it to terminate to optimality. If you stop in between and you obtain some feasible solution, it might not be an optimal solution. So for example, in that maze problem, we saw that we are doing depth first search. And suppose you obtain one solution to the from start to the finish, and you're not looking for other solutions, and you terminate the algorithm in between. So you may have a route from the start to finish, but that might not be the optimal route because you did not search the whole space. So that is a heuristic algorithm. Although you were using a depth first search, which is an exact method, but you terminated it prematurely. Okay. Is that clear? Now we will talk about state space search, state space landscape. Okay, so what is this? So I'll just go to the diagram and it will be better. So you see over here I have given you what is known as a state space landscape. So what does this mean? So you see over here I have a function f of x, y is equals to f of x. So this is a one-dimensional problem where the search space is of one dimension and the objective space is also of one dimension. So you have only x and this x influences y, and you are trying to, just a minute. Okay, sorry. So what I'm saying is over here you have one dimension problem which is x, and this x influences y, right? And this x constitute, so this line constitute the search space, this is the search space, and this y constitute the objective space. So you can recognize this as using that calculus, right? So over there, if you try to minimize or maximize some function, what you do is you take the first derivative and then you obtain that point, saddle point, or it can be a global minima or global maxima, and you check using the second derivative. So over there also you are doing optimization. You are trying to find that point x which minimizes or maximizes y, right? So that is the same idea we are using here, but over there we had some assumptions or some cases that the function should be continuous function and should be differentiable, and you do not have any constraints. In this case, when we are talking about here, we may have non-continuous function, non-differentiable function. You can have constraint. For example, x can be in between these two. You cannot have x outside these two ranges. Then what is the global minima? Then what is the global maxima? That kind of situations we are seeing here. And then you cannot use the concept of that differentiable and checking what is the optimal point. Okay, so this is what a state space search looks like. And you see over here this point and these points are local minima, and this is the global minima, right? Similarly, this point and this point and this point are global, not global, local maxima, and this point is the global optima, global maxima. Is that all right? So over here I have a one-dimensional search space and one-dimensional objective space. You can expand this as much as possible, but you may not be able to visualize. So for two-dimensional search space and one-dimensional objective space, you can even visualize that also. So suppose this plane of the paper is the search space. So you have x1 and x2, right? x1 and x2. This is the search space you have. And what is where will be this curve? Where will it be? It will be a surface over this, it will be a curved surface over this plane, right? So that surface, any point in that surface will give you the objective function value. Is that all right? And imagine in that case you have a discontinuous curve. Moreover, you have some constraint that you cannot have um, that search space cannot be outside some bound, and therefore it becomes more and more difficult. So this is a two-dimensional search space. You can go for n-dimensional search space. Over there you cannot imagine, you just have to work with mathematics. Now, okay, I'll go forward. Is that all right? Okay, so we have talked about search spaces. Before going to neighborhood, what is the idea of single solution metaheuristics? So we will talk about S metaheuristics. So what is S metaheuristics? It is known as a single solution metaheuristics. What it will do is it will pick one solution. So suppose it is picking this solution. This solution it is picking x1, and this is the functional value, objective function value at that point. And what we are trying to do is we are trying to minimize. So it is a minimization problem. So what it will do is it will look into the neighborhood. So we have not talked about neighborhood. For this case, the neighborhood is just the two sides it can go. Either it can go a little bit on the right or it can go in a little bit in the left. So that is the neighborhood for this case, right? So it can either go this way or this way, a little bit. And if it is a minimization problem, what local search? So we are talking about local search now. And it is a single solution meta-heuristic because we are working with a single solution. Currently we have one solution which is x1 and we are trying to minimize. So what it will do is it will look into the neighborhood. So over here the neighborhood can either be in the left hand side or the right hand side because it is a real valued function. So real value. So x belongs to r, right? Over here it is a real valued representation. So you can either have plus delta on the right hand side, minus delta in the left hand side, and so on. Right now you see, since it is a minimization problem, it will pick this part, this one. So this will be the new x. I'll writing as x1 dash. And again, when it has come to x1 dash, it will look into the neighborhood. So it will go either this way or this way, and it will see that this is this side. So going to the right hand side decreases the objective function value. So it will come to x1 double dashed, and then it will come to over here, suppose x1 triple dashed. Now when it has reached x1 triple dashed and it sees its neighborhood on the left hand side and the right hand side, it sees on the both sides the objective function value is increasing. Therefore, what it will say is it has reached a local minima. It will not guarantee that it has reached a global minima because you can see that this is the global minima. And suppose if you were starting with this solution, so in that case you could have reached the global minima. That is why it says that it doesn't guarantee optimality. You may get stuck in a local minima. So this is how a local search works, by the way. Is it clear? Okay, so since this is clear, I will emphasize on the fact that over here, the solution space or the search space was a real valued space, and therefore thinking about neighborhood was easy. So you just had to subtract a small quantity to the left and add some small quantity to the right. It was very easy to think about what a neighborhood is of a solution. Over here, suppose the solution was 3.5. So the neighborhood of this x1 can be 3.4 comma 3.6. So this is one neighborhood. So n of x1. So this is a neighborhood of x1, right? 3.4 and 3.6. Any point in between these two ranges is a neighborhood. But suppose it is, so we are using a representation as permutation representation. So A, B, C, D, E, F. So for the traveling salesman problem, this is my representation. Now you tell me what can be a neighborhood of this solution, because this is also a solution. We talked about this, that this is a solution to the problem. Now, how would you think what is a neighborhood of this? Because to do local search, you have to have the concept of neighbors. If you don't have the concept of neighbors, you will not be able to use local search or any kind of meta-heuristics per se, because you have to go from one solution to the other with some connection. And if you don't have that, you will not be able to use any kind of heuristic or meta-heuristics, provided it is not, yeah, neighborhood is important. Is it clear? So we'll talk about neighborhoods. Right, so we will talk about neighborhoods. Okay, so what we'll do is we'll take 5 minutes break, and before we go for the break, I'll tell you I don't think I'll be able to complete whatever I have planned for today. So I guess I will carry forward the remaining part, and we will have a extra class on this Tuesday, and then we'll cover this, and maybe exact method I can take on Sunday, next Sunday. So we'll meet at after 7:15. Okay. And if you have doubt, you can ask me in this break, by the way. All right. So, okay. So we'll talk about neighborhoods. Now, generally, when we say neighborhood, we we mean that a very small change in the solution. So we don't generally drastically change the solution. Okay. So whenever we have a very small change to a solution, then only we will say that this is a neighbor of a solution X. Okay. So set of solutions that can be reached from a given solution by making a small modification. And there are ways to measure how small the modification is. So that is known as distance. We will not talk about that here. But in this real valued function, you have the distance. You see over here, you can say 0.1 is the distance between 3.4 and 3.5. But when we have other representation like binary representation, permutation representation, and other representations, the concept of distance are will not go into over there. But nevertheless, there should be a small modification. So what are key characteristics? Define the scope of, okay, yeah. So we'll talk about just the and how to obtain neighborhoods. So suppose so you can define a neighborhood, right? So you can define a neighborhood. Suppose you have A, B, C, D, E, F. So this is one solution. Now, if you have a permutation representation, there can be different ways to create a neighborhood. And again, the concept of distance comes. So one neighbor can be a lot further away from the other neighbor. And you might not be able to think that as plot. So over here in the real valued, you are thinking about as plot. So, but over here, you might not be able to visualize that plot. So one neighborhood can be swap. So over here, what I will do is I will swap D and F. So it can be A, B, C, D. Sorry. Let me take one page for this. So what I'm talking about is traveling salesman problem, permutation representation. Okay. So A, B, C, D, E, and F. So this is the representation. First, I'm talking about swap neighbor. So you can just swap any two cities. So it is, you can have A, E, C, D, B, and F. This is one neighbor. You can swap any of the cities A, F, and more options are there. Second is insertion. What is insertion? Insertion is you pick one of the element and put it in some other location. So over here you can do A, F, B, C, D, E. So what it is doing is you're picking F and putting it in between A and B. This is one neighbor. And these two neighbors, so the distance between these two neighbors and the distance between these two neighbors are different. One may radically change landscape. So over here we are talking about landscape, right? So what is the, so this is known as the landscape, right? The objective function landscape. And changing from one neighborhood. So this is known as swap neighborhood of this representation. This is known as insertion neighborhood. So different neighborhoods can have different landscapes. Other can be two opt. So two opt. So what is two opt? So you see you have creating the this is this will be easier for two opt. A, B, C, D, E, F. So your neighbor was so your solution was this A, B, C, D, E, F. So this is your solution, right? So what two opt does is two ops removes two edges. So it will remove this edge and this edge, and it will do like this. So it will go here, it will come here, and reverse these edges. So this is two opt. So what will happen is your solution was A, B, C, D, E, F. Now your solution will be A, B, E, D, C, F. So what it is doing is between A and F, sorry, it between B and F, it is क्या बोलूं, it is changing the order. So it was CDE, now it has become EDF. So you see, you focus over here, it was CDE, it has become EDF. So this is another neighbor, two opt neighbor. So there are many ways to create neighbor. This is what I am telling you. Okay, there are many ways. So some neighbors are good for, so for traveling salesman problem, two opt neighbor are very good. Okay, so when you are solving a traveling salesman problem, two opt neighbors create good neighbors. But if you are solving a sequencing problem, suppose you are solving a scheduling problem. So for scheduling problem, two opt neighbors are very bad, very bad. In general, in that case, we use swap neighbors or insertion neighbors. although both are using permutation representation. Okay, although both are using permutation representation, some neighborhoods can be better for a class of problems, some neighborhoods can be worse for a class of other neighborhoods are good for some class of problems. Okay, so these are some technicalities. If you go into depth of these fields, you have to learn those concepts. Okay, so we talked about permutation neighborhoods. Then we talked about binary representation. So when we have a binary representation, so suppose we are talking about the knapsack problem and there are 7 objects and you have this solution. Okay, so this is one solution. So a neighbor can be flipping any one of the elements. So suppose a neighbor can be 0 0 1 0 0 1 0. So flipping just one, or a neighbor can be 1 1 1 0 0 1 0. Okay, so flipping one can be a neighbor. So you can flip two at a time. So over here we are doing one at a time. We can do 2 at a time, 3 at a time, and so on and so forth. So more you are increasing, suppose you are doing 5 at a time. So that is a very far away neighbor, and you are saying that we will go from one solution to that solution. You see, you are drastically changing a solution. So suppose this was close to one local optima, and what you are doing is you are drastically changing that solution. So suppose this was the landscape, and suppose you are here, and when you are drastically changing the solution, you may just jump to this point. But if you're just changing one at a time, you can be very close to this. You can come over here. So this is the idea of using different kind of neighbors. Some neighbors can have very small distances, some neighbor can have a large distances. And what do you mean by distance over here? I'm not going to that, but the idea remains the same. Is that clear? Any doubt? Okay. So yeah, so we have talked about this permutation representation, binary representation, and continuous. So we have talked about what a continuous is. A well-defined neighborhood structure is crucial for the success of the meta heuristics. If you don't have a good neighborhood definition, then your meta heuristics might perform very poorly. So I was telling you, for a traveling salesman problem, 2opt gives very good neighborhoods. Okay, so yeah. So I can give you some idea. Okay, what is happening? I can give you some idea. So when you are saying, suppose swap neighbor, so the landscape can be very erratic like this for the traveling salesman problem. But when you are doing a 2opt neighbor, the landscape becomes like this. And that is why 2opt neighbor is better for traveling salesman problem. Something like that, some idea, something like that. Is that clear?
This last part is not clear. This last.
I know. I know. Okay, so what I'm doing over here is, you see, I'm saying this is one solution, x1. And when I say 2opt neighbor, so generally we place neighbor close to that solution. So we are saying this is that neighbor, which is x2 in this in this neighborhood. Okay, but in the same thing, if you map over here, suppose x1 was over here, x2 could have been here. So what does it mean? So you see over here, A, B, E, D, C, F. And originally x1 was, what was x1? A, B, C, D, E, F. So from this solution to this solution, if you want to go using swap neighbor, how many swaps you have to do, you see. So first swap will be you swap. Okay, so make it a larger 2opt. Suppose the larger, because this is very close to each other. What you do is, if you swap C and E, so A, B, C, A, B, E, D, C, F. So one swap will give you this 2opt, but suppose the length of the city was large. So, and I'll give you another 2opt. So suppose the 2opt was, you just keep A and F same and just alter everything, E, D, C, B. Okay, so this is the 2opt. What are you doing is, you're keeping A and B, A and F the same, and altering B, C, D, and E. So this is one neighbor of this, right? 2opt. Now you see how many swap moves you have to do to reach this 2opt. First, what you have to do is, you do swap of B and E. So first swap 1. What you're doing is, you are swapping B and E. So A, E, C, D, BF. This is one swap, the first neighbor. Then the next neighbor you have to swap D and C and D. So you will have A, E, D, C, BF. So you see over here you have to go from one solution to its neighbor and then its solution to its neighbor. So what you are doing from x1 you are going to x1 dashed, and then from x1 dashed you are going to x2. But in this neighbor, 2-opt neighbor, you are just going from x1 to x2. So you are placing x2 very close to x1 in 2-opt. But in swap neighbor, x1 and x2 are farther apart. So the points, functional points, are at different points. So you see the objective function values curve changes on where you are placing x1 and x2. So for swap neighbor, x1 and x2 are farther apart. But for 2-opt neighbor, x1 and x2 are very close to each other. And that influences the curve of the objective function, and that the landscape changes. I hope I'm making sense.
So you are saying that the formulation is changing the overall objective function so that it can reach to the optimal solution. Not,
No,
not
no,
like
no,
that.
no. The objective function is not changing. So I'll reiterate everything what I have said. What is changing is how the objective function is curving. Suppose this is a large, suppose I'm not take only 6 cities. Suppose this is a 15 city problem. A, B, C, D, so on and so forth. Suppose that 26 city problem. Now what you're doing is for 2-opt, any 2-opt is close to each other. So over here, the landscape for x1 to reach x2, we are saying it is one step. So from x1 to x2, it is just one step. So the objective function value of x1 is this, and objective function value of x2 is this. It is same for swap also. So for swap, you from, so this is the solution, x1 is this, and what is 2-opt? So suppose you are changing everything in between. From B to Y you are changing. So you have A, Y, X dot 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 C, B, Z. So for 2-opt, x1 and x2 is just one step away, right? But for swap, you have to do 13 swaps. So you have to swap B to Y, C to X, and so x1 is over here, but x2 is far, far away. So the objective function value of those two are very far away. So that changes how the objective function behaves in that landscape of the objective function changes. So these neighborhoods are defining how your search space is. In one neighborhood, x1 or x2 are very close to each other. In another neighborhood, x1 or x2 are very far away from each other. And that changes how your curve of the objective function is over the search space, right? These are advanced concepts, by the way. If you're not able to understand this, all right. Since we are here,
But
then we are talking about this.
this means the objective function remains same, but our steps is changing so that from one step to another step, high good jump may be there or less jump may be there.
Right.
Means
So
our searching step is changing
yes.
on in the same objective function.
Yes. So when you do local search, so for swap neighborhood, you will just see these areas, and over here for the swap 2-opt neighborhood, you will see these areas. But you see the objective function value are different because the neighborhoods are different, and that is why 2-opt neighbor is better for traveling salesman problem, because that gives a neighborhood something like this, very a well type of neighborhood. And local search is very good for traveling salesman problem when you are doing 2-opt neighborhood, because if you just do local search, you will not get stuck into local optima. There are very few local optimas. You will go to a global optima. So defining a neighborhood is also very important in such kind of heuristics, meta heuristics. And again, I'm telling you, if you're not able to understand this part, it's all right, because this is advanced concepts of this topic.
Okay, it's fine.
Any doubt?
Shubham,
Yes.
hello.
Yes, I can.
Yeah. If if I am aware of the sample space, then why do I need to find out local minima or a local maxima? directly, shall I not go for global minima or maxima?
Sorry, what are you
This,
talking about? Sample space, search space, right?
search space. In this, in that sinusoidal waveform, will you please come to that sinusoidal waveform? No, on the slides. On the slides.
Okay, okay, here. Hmm.
Yeah, yeah. If in the solution space and solution space and objective values, if this
Hmm.
waveform in the sense, if these values are known, then why do I need to go for local minima or a local maxima?
So you see,
Do I uh, optimize it? Hello, Shubham.
yes, you're audible. You're audible.
Shall I say that optimizing means in this instant case, optimization means finding out global minima or a global maxima?
You see, you are somewhat correct, somewhat wrong. So I'll again tell you everything what you are saying. You see, we actually don't know this curve. We know the function. We know just कि एक representation है, उसको add करेंगे तो it will give me one value, right? We don't know this curve in the start. If we know the curve, so
Will
what
you
you
please
have to.
repeat? थोड़ा fast हुआ. Will you please repeat it?
Yes, I am saying is we don't know this curve. This curve
Okay.
we don't know exactly. Whenever we get one solution, we can calculate the value at that solution. So for each solution, you have to get what is the functional value. That is what exhaustive search is. कि आप हर एक solution में जाइए, find its objective function value, and then what you do is when you have exhausted all possible solutions, you will know what is the best solution. That is what exhaustive search is.
No, let me ask you, if we don't know this curve, let us assume that if we don't know this curve, huh, and let the search begin with solution space at the origin 0 0.
Okay.
The very next neighborhood would tell that the initial let that x0 is less than x1.
Okay, so this is x1.
So the search will continue for finding out minimum value. Let's not call local or a global. Let's
Yes.
not call local or a global. The search will continue until it reaches its peak value. Let that be xp. Will you please denote that xp?
This one.
How can I can't see your marker? No, 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 no. First peak. First peak.
Okay, this one.
Yeah,
XP.
absolutely. For the very next nearest neighborhood, let that be xp1 plus 1. The value of xp1 plus 1 is less than xp, correct?
First, tell me, is it a maximization problem or a minimization problem?
Minimization. Had
Minimization.
that
Okay.
been a maximization problem, then the search would have been stopped at x1, correct? Because
X.
x1 is greater than x0.
No. No.
Objective value of x1 is greater than x0.
But again, you will look at its neighborhood from X1. So you will go to
No,
X.
that's what my question is. If the algorithm finds x1 value of x1 greater than value of x0, then why shall it look for next neighborhood? Because it already have achieved from its
Acha,
perspective, it already have achieved the maximum value.
I understood. You see, we have not talked about local search. That is why you are getting confused. The next slide which I have is about local search.
Okay.
Okay. So I will just explain your question over here. So how local search works. So I'll just go to the algorithm. Okay,
Okay.
not algorithm. I'll just show you how this local search works. So you see, local search will only terminate. So when will local search terminate? Local search will only terminate if it cannot find a neighbor better than itself. Okay? Local search will terminate if it cannot find a neighbor better than itself. So suppose it started with, it is a maximization problem. Suppose it is a maximization problem
Hmm. Okay.
and it has started with x naught. Now it will look for its neighbor. So in this side there is no neighbor, so it will look here. So suppose this is the neighbor and this neighbor has a better objective function value than x naught, therefore it will
Yeah.
move to x1. Now
Okay.
x1 will be my current solution
Yeah.
and
Then
local will again look at its neighbor.
So is it necessary that even though from x0 perspective, even though x1 is greater, x1 has to go for one more neighbor?
नो नो,
So
इट विल, देखो, अगर एक सोल्यूशन से दूसरे सोल्यूशन हम लोग चले गए, राइट, देन वी माइट आल्सो हैव उससे भी बेटर, सो वी विल कंटिन्यू डूइंग इट अनलेस वी विल नॉट बी एबल टू फाइंड एनीथिंग एल्स बेटर. दैट इज द आइडिया ऑफ लोकल सर्च, कि मैं कंटिन्यू करता रहूंगा लोकल सर्च until and unless I will not be able to find any better neighbor in my neighborhood.
So in this case, because we are unaware of the waveform,
Yes.
how could we come to know that the search will stop at the first peak to obtain the local maximum?
So when I am here, suppose I am at x5, I will check this and this, so I'll move to x6. Okay?
Yeah,
So I have
correct.
now from x6 I will see x5 and x7,
Hmm.
and I say कि x5 भी x6 से कम है, x7 भी x6 से कम है, so there is no neighbor I can move to.
Okay, yeah, I got it. Means despite first search maybe हमें first in the first search x1 is greater than x0, it has to cross check that whether x2 is less than x1 or not.
अब सिर्फ x2 नहीं, there can be multiple, there can be x, बहुत सारे n neighbor हो सकता है उसका.
So where this local search has to stop? If in this case, if you are saying that there can be n neighbors which can have maximum values, then where this search has to stop?
So at every point, so जैसे मान लीजिए कि we are at x1, over here I am saying it has two neighbors. So suppose it has n neighbors, so it has to search all n neighbors, and in all n neighbors, whichever is the best neighbor.
One sec. N neighbors in the sense in the same two-dimensional space, correct? Not n-dimensional space.
No, no. If you are at two dimensions, यहाँ पे भी you can have n neighbors, by the way. So suppose you are going for 0.1 fraction, but neighborhood you are checking for 0.01. So from 0.34 to 0.36, you will have 0.41, 3.41, 3.42, dot dot dot, 3.58, 3.59, and 3.60. So 3.5 ka you have over here 19 neighbors, right?
Correct.
So all 19s you have to check, and whichever is the best, you will have to move to that neighbor.
Okay.
And from that also you have to check again 19. If there is no best, then you will say ki, I have reached the best.
Okay, Shubham, for the sake of understanding, let's name the peaks as P1, P2, and P3. Will you please do it?
Correct. I am doing it. So this is P1.
Yeah, correct. P1,
P2,
and P3.
P and P4.
Okay, P4. Yeah. When we begin with 0, 0, means 0, 0 point, where exactly the search will stop at P1 or at P2 or at P3?
So it depends upon the distance you are taking from the point. So if your distance is this much, so suppose your distance is only this much, so it will stop at P1. क्योंकि इससे ज़्यादा it is not getting any better. But if your neighborhood is very large, so suppose your neighborhood is this much, this much is your neighborhood, so you might, so not here, sorry.
No, okay, just next to P3.
हाँ, मतलब you have to.
I got it. So the range is important thing while calculating the maxima, minima optimization problem.
Right. So suppose you have increased the neighborhood to the search space. आप बोल रहे हैं कि मैं पूरा neighborhood अपना search space बना लूंगा. So that is an exhaustive search. So you are saying कि मैं सब solution check करके I'll go to the best. So that is an exhaustive.
In that case, shall I say that if I do exhaustive search, I'll get the global maxima?
Right. So what you are doing is कि exhaustive search नहीं करके you are constricting the neighborhood. कितना बड़ा search space नहीं रख के I'll just constrict it to my just बगल वाला neighbors, and then I'll move to that.
तो ना मुझे एक, then I have one question in my mind. Then why not to go for exhaustive search always?
Exhaustive
so as to
search,
obtain the global maxima.
Exhaustive search is expensive.
In one shot.
It is expensive. You have to calculate. So यहाँ पर it is infinite number of neighbors यहाँ पे solutions है. It is very expensive to calculate objective function value for, suppose infinite नहीं है 1 million. So you have, it is very expensive to calculate objective function value for 1,000,000 points.
Okay. 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 Got it. Got it. Okay.
Any doubt? Okay, so we will just move on. So what is local search? I have given you everything. Maintains a single state, so it is important, huh? It only remains at a one point. That is why this is known as single solution metaheuristic. Okay, it only sticks to one solution and moves to its neighboring state. It gives you good enough solution. Example, I have shown you traveling salesman problem. This is the algorithm. So what it does, it starts, and by the way, I did not mention this, it is the starting point is very crucial for this algorithm. You see in this graph, if you start from this point, then you may reach to the global optima. You will not know that it is global optima, but still you will reach the global optima. But if you start over here, you may get stuck to local maxima. So the starting state, how you're determining that, is also crucial. You may use some other ideas from some other algorithms. So suppose what you did is you are doing, I'll just give you one example. So you are doing exhaustive search, and suppose that not exhaustive search, you're doing some exact method, and that exact method would have taken 3 days, and you don't have that much time. So what you did is you terminated the exhaustive search, or not exhaustive search, exact method at 1 hour time point, and you obtain that feasible solution. And from that feasible solution, you are saying that I will start local search from this point. That will be my point of start. So that is, you're combining exact method with metaheuristic, and that exact method was a heuristic, by the way. You terminated it in between, so you are picking that feasible solution from the exact method, terminating in prematurely, and you are saying from that point I will do local search. So that is one initial point you can have. You can have randomly. So for a traveling salesman problem, you can randomly generate one tour, and then you can start doing local search. So this initial point is important. You can do so something known as iterated local search. So I'm just talking about local search. In iterated local search, we randomly generate multiple initial solutions. So what I will do is I will start from this point first and I'll do local search. I'll start from this point and I'll do local search. I will start from this point and do local search. So multiple local search I will run, and I'll pick the best local optima I have obtained, right? So that is known as iterated local search. There are many variations of local search, by the way. So this is the basic local search. You will start with one solution until the termination criteria is met. What is my termination criteria? You can have ki there is no neighbor better than this. You can also have time limit. So you can just say ki 10 minutes se zyada I will not do local search. So there can be different kinds of termination criteria. You generate the neighbor. So you have a point S naught जिसको आपने S में store कर लिया है. So S naught has been stored to S. And what is N of S? N of S is the neighborhood of S. If there is no better neighbor in N of S, N of S में there is no better neighbor, then you stop this algorithm. Else, matlab you got a better neighbor which is S dashed. Okay, S dashed is a better neighbor. S dashed is a better neighbor in the neighborhood N of S. Then you change S to S dashed. You just go to S dashed, and then you again find its neighbor, find if there is a better neighbor or not, and then you just repeat everything. Okay, so this is local search. And whatever I am teaching you, I have taken from this book, by the way, and this is a very, very, very brilliant book. I have it with me. This is this book. This is a very, very good book on metaheuristics. Huh? Okay. So yeah, traveling salesman problem. I have given one example of traveling salesman problem. Local search we are doing, and we are doing two swap. So we are just swapping. Huh? So we are starting with A, B, C, D, E, F, and we are just swapping. So over here the representation has A at the end. You can just ignore it, by the way, doesn't matter. And swapping kar rahe hain. So what will it do is A, B, C, D, E, F. You can just swap. So B and C are swap, C and D are swap, D and E are swap, and you are creating swap neighborhood. And one more thing, which is very crucial. If you are doing one kind of neighborhood, you will stick to that neighborhood. You will not change the neighborhood. If you are saying I will do swap neighborhood throughout my local search, so you have to do just swap neighborhood only. If you are saying I'll do two opt neighborhood, you have to do two opt neighborhood only. Okay, in local search there are other algorithms which can incorporate various kind of neighborhoods, जिसमें आप swap neighborhood भी search कर सकते हैं, insertion neighborhood भी search कर सकते हैं, to opt neighborhood भी search कर सकते हैं. Those algorithms are known as variable neighborhood search. ठीक, so those are other algorithms. In local search we only stick to one neighborhood. That is important, huh? So yeah, this is one example. Okay, so this is one example, and whatever we have talked सब वही लिखा हुआ है. You just go read. If you find any doubt, you can just ask me in the next class. And now we will come back to that intensification and diversification. If you remember, I skipped one section when we were talking about meta heuristics, exploration and exploitation. I'll just go back maybe. Over there we skipped one part when we were talking about this over here. You see, exploration and exploitation, intensification and diversification. We skipped this part when we were talking about meta heuristics. So we'll go to that slide and we'll see what it is. Okay, so what is intensification and diversification? You see, when we are talking about intensification, it means that you have a solution and you are only focusing on that solution. Like local search. Local search क्या करता है? It's very local to that point. It only search its neighborhood. Only search its neighborhood, right? It is very localized, and that is known as intensification. You have one solution and you focus only in that vicinity of that solution. And when this helps, so suppose you have found out some good solution. For example, you have used that exact method, terminated it prematurely, and you are using intensification. Why? And you are using local search. Why? Because you are saying कि ये solution which I have got from that exact method, it seems to be good solution, and I'll use that solution and I'll only intensify. I will only do local search around that point. So it will only do intensification, and local search only does intensification. It does not do diversification. Okay, so local search is an algorithm which only does intensification. सिर्फ local points देखता है and moves to that local point. Local point देखता है, moves to that local point. It sticks to that area. What is diversification? So diversification is exploring the whole landscape. So for example, I am running local search with multiple random solutions, like the example I gave you, iterated local search. So I'll start from this point and I'll do local search. I'll start from this point and do local search. I'll start from this point and do local search. That is diversification. I'm diversifying my search over the whole landscape. So क्या होगा? I am first randomly I have picked this point. I have done local search in this area. Randomly I have picked this point. I have done local search in this area. Randomly I have picked this point and I have done local search in this area. So I'm diversifying using that randomness. I'm saying I'll start with some random point and then do intensification. क्या हो रहा है? I am picking this point and I am doing intensification around that area. Again, I am doing diversification by picking another random point and then I am doing intensification in that area. So these two come hand in hand. If you don't diversify, you may get stuck into local optima. So you should diversify in some way and intensify when you think ki this is a good solution. So both are important. Diversification also important and intensification is important. I'll give you one example when diversification can be bad. So suppose you have done exact method, you have obtained a solution and it is very close to the global optima. But what you did is you did diversification. You forgot that point and you moved to some other point. That may be bad. So sometimes diversification and intensification, you should be careful when to diversify and when to intensify. And there is a trade-off. There's a balance between these two. Either you can intensify or you can diversify. You cannot do both at the same time. There are some algorithms which tries to do both at the same time, but strictly speaking, दोनों साथ में it's difficult to do. ठीक है? Any doubt? By the way, whatever I'm teaching, it's clear, right? Because these are new concepts over here, different from what we have learned before this, right? Okay. Nevertheless, these are all methods to solve a search problem. So these are algorithms in some way. So this local search also we have shown some algorithm, right? So you can write a code to do local search. So remember that, huh? Now we'll talk about simulated annealing. Okay. So what is simulated annealing? Simulated annealing is very similar to local search, except यहाँ पे हम लोग randomness ऐड करें. We are adding some kind of randomness in this. ठीक है? It is also a single solution metaheuristic. That means it focuses on only one point itself. There are other methods where we have population based metaheuristics. We'll talk about it. But currently, this is a single solution metaheuristic. Huh? So what is the idea of simulated annealing? So in metallurgy, this algorithm is actually inspired by annealing. What is annealing? Annealing is when we have some material, some metal, it is heated to very high temperature and then it is cooled. By doing so, the atoms of that element are aligned in such a way that strength बढ़ जाता है वो material का. And over here we are doing simulated annealing. So we are simulating the process of annealing to do some search. That is why this method is known as simulated annealing. Okay. So what are we doing? So you see, when we heat a metal, the randomness in the atoms are very high because it is in a very high energy state. So the atoms are very randomly moving from with one another. But when the temperature decreases, that randomness decreases. So the movement decreases. So that idea is being used over here. What is the idea? Whenever you are beginning to do in this process, simulated annealing, you do diversification. You randomly go here and there, here and there. Not a lot. I'll show you how diversification is being done. But whenever you are starting, you randomly do some here and there search. But as the time progresses, dhire dhire, you have to intensify. Pick one point which is good, you think it is good, and you stick to that point and do intensification. So simulated annealing, starting May does diversification a lot and intensification very, very less. As time progresses, it reduces diversification and focuses on intensification. That is the whole idea of simulated annealing. Any questions? We will see how it does, but this is the idea. Is that clear? Any response? Okay. Okay. So yeah, this is all what I have written over here. So what I will do is I will not read all those things. I'll just use sketches to explain. Okay. So what it is doing is, suppose this is my landscape. This is my landscape. And what I'm doing is I'm maximizing. So just a minute, what I'll do is I'll create a landscape which has good variations. So this is the global maxima. This is my global maxima. Now, suppose you are doing local search. So what we did is we picked one solution randomly. So suppose we are picking this solution randomly. Now, local search will come to this point and it will stop. It will come to this point and stop, right? But what simulated annealing does is, whenever you are at a point, suppose you are at a point x naught, and you find its neighborhood, which is n of x naught, all possible neighbors. What is n of x naught? N of x naught is the set of all neighbors of x naught, and we are calling it as neighborhood, right? So simulated annealing, what it does is it checks the neighbors one at a time. Local search भी वही करता है, by the way. It checks. So यहाँ पे I have taken one example, right? Okay, so we had points, right? 3.41, 3.42, dot, 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 3.58 and 3.59 and 3.60. These are the points. So what local search will do, it will exhaust this neighborhood. It will search all points in this neighborhood and it will pick the best point. This is what local search does, by the way. Neighborhood को पूरा exhaustively search करता है, not the search space, only the neighborhood. What simulated annealing does is it checks one neighbor at a time, जैसे local search करता है. But if that neighbor is not improving, it is having some probability. So suppose it is at 3.5 and functional value of 3.5. So for a maximization problem, this is more than functional value of 3.41. So what local search will do, it will reject 3.41. It will say 3.41 is bad. Don't pick 3.41 because I have a better uh, point, which is 3.5. But what simulated annealing does is it will say, okay, 3.41 is bad. But what I will do is I will have a probability. So with some probability, you see, do you want to reject it or not? So suppose with 70% probability, I will reject a not good solution, and with 30% probability, I'll pick it. So this 3.41 has some probability of getting picked. क्या होगा इससे? What will happen? So you see, suppose you are at this point. Just a minute. Suppose you are at this point x1, and when you are at this point x1, you see कि both of the neighborhood, all the neighborhood is bad, so local search will terminate. But what this simulated annealing will do is it will check its neighbor, and there is some probability to go to that neighbor. And during the start of the search, that probability is very high. So suppose with 90% probability, it can go to a worse neighbor. And जैसे जैसे time बढ़ता जाएगा, it will decrease that probability. It will go to 50, it will go to 40, it will go to 30, it will go to 20, and at the जैसे जैसे कम होता जाएगा, the probability will decrease. तो क्या होगा ना, it will accept worse solution with some probability. So there is chance कि वो यहाँ धीरे 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 यहाँ आके it can go to this area, and then it can go to a global optima. So because of this uncertainty, because of this probabilistic selection, there is some chance कि you can escape local optima. Local search में there is nothing to escape local optima. If you are stuck in a local optima, you will be stuck in a local optima. But simulated annealing में there is some probability कि आप local optima को skip करके आगे बढ़ सकते हैं. That is the idea of simulated annealing. Any questions? So whenever it is searching the neighborhood, एक worse solution को भी pick करने का there is some probability. It can pick a solution with some probability, a worse solution. That is the idea, and I'll give you the expression of that probability. But this is the core idea of simulated annealing. Any doubt? Okay, so I am assuming there is no doubt. Now the probability with which it picks a worse solution is given by probability E of delta is equals to E delta E by T. Just a minute, it should be minus delta E. एक minute, I'll just check. Yes, it is minus delta E. So I'll just correct it. It is minus delta E by T. I'll correct it and then send you. Not this one, but the one which I am not editing. I'll change that and I'll give you. It is probability delta E to the power minus delta E by T. I'll tell you what delta E is. I'll tell you what T is. But this expression comes from the original process annealing. जब annealing करते हैं metal में, this expression is there. So from there, this expression has been picked. Now coming to what delta E is. Delta E is only change. So suppose we are at x1 and x2 is the neighbor. So delta is the change in the objective function. Change in the objective function value. That is what delta E is. And what is T? T is the temperature. So in simulated annealing, when we start with a very high temperature. So suppose we are starting at 12,000 degrees centigrade. And what we'll do is as time progresses, we'll decrease this temperature. We'll go to suppose 100 degrees centigrade or something like that, or 80 or 20, something like that. So we have to know how we will change this temperature. Initially, we'll start with a very high temperature and then we'll decrease the temperature. And if you see this table, you see this is delta E. And yeah, ये plus होना चाहिए, by the way. The expression is e to the power minus delta E by T. So this is the probability. So what is happening is जैसे जैसे temperature कम होता जाएगा, the probability of accepting is decreasing. So ये सब values are probability, probability of delta E. So over here you see if delta E is 1 and temperature is 10, the probability of accepting a worse solution is 90%. But if the temperature is 5, the probability of accepting is only 0.82, and then it decreases to 0.37. And you see as delta E increases, मतलब क्या हो रहा है? What is delta E? Delta E is f of x2 minus f of x1. इसका मतलब you are going to a worse solution. मतलब 3 का difference है, पहले सिर्फ 1 का difference था कि चलो ठीक है worse है, it's only by 1 unit, but over here worse है by 3 unit, so that is also affecting, the temperature is also affecting, and the difference in objective function value is also affecting. Okay, so both of the things together affects the probability with which you will accept a worse solution. And yeah, so this is the algorithm. I'll just go through it once. So S naught is your starting, again you need a starting point, huh? In local search also you need a starting solution, initial solution. Over here also you need an initial solution. You set T max to some value and you store it in T. If the stopping criteria is not met, it can be time. So suppose you are giving 10 minutes to run this algorithm. Not equilibrium condition. So this is like reaching the minimum temperature. So you are saying when you reach a temperature of 20 degrees centigrade, you will stop the process. So this is what equilibrium condition is. So equilibrium says that 20 degrees centigrade is my equilibrium temperature, and I'm starting with suppose 1000 degrees centigrade. So that is my starting point, and equilibrium point is 20 degrees centigrade. And this G of T tells you how to decrease the temperature. So suppose we are decreasing linearly या फिर stepwise. This G of T will tell you कि 1000 के बाद कौन सा point लेना है. It can be 800, it can be 700, it can be 500. So G of T is a function which tells you कि with each iteration, you see you are doing iteration, right? So with each iteration, next T का value क्या होगा? So we are starting with this S naught. We generate a neighbor. We calculate delta E. And if delta E, by the way, if delta E is better, matlab, if it is a good solution, we will always go to that good solution. But if it is a worse solution, then there is this probability with which we'll go to that solution. What it means, if I am here and I am searching, so the first neighbor I search was a good solution. So if it is a good solution, I will always accept it. But if it is a worse solution, then only I'll do the probability thing. मतलब अगर हमको good solution मिला है, I will always move to that good solution. With probability 1, I will move to that solution. But अगर एक worse solution मिला है, I'll have some probability to moving to that solution. So that is what it is saying over here. If this solution is negative, move to that solution. That is, you are decreasing the objective function value. ये minimization problem के लिए लिखा हुआ by the way. So move to that solution. If not, then accept the new solution with some probability, right? And then change the temperature and again repeat the process. Okay, so this is the idea of simulated annealing. When you stop, then you give the best found solution. Okay, so this is it for single solution meta heuristic. Next we will talk about population based meta heuristic in the next class. So I should have written population based here. Any doubt?
This previous slide.
Yes.
How this whatever that probability we are mapping to a particular, if not it is being accepted, and then next iteration how that point will be considered. Okay, we got some probability mapped to that particular solution, but next iteration or how will it be considered in the algorithm?
I'll tell you. So you see, suppose ऐसे लिखने से अच्छा होगा. So you see, suppose n of, so we are at x1, and suppose this is x11, x12, x13, x14 dot 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 x1n. So we have n points in the neighborhood of x1. ठीक है? So what this simulated annealing will do is it will pick one random neighbor. ठीक है? It will pick one random neighbor. Suppose it has picked x13. This is the neighbor it has picked. It will see if it is better than x1 or not. Better मतलब अगर maximization है तो उसका objective should be more, minimization है तो इसका objective should be less. So it will pick x13 from this neighborhood randomly. So you see it is written here, generate one random neighbor s dashed. So it is picking randomly one neighbor from this neighborhood. If it is good, if it is a good solution, then it will move to x13 and then it will generate x13 and iska neighborhood generate hoga. It will go to that solution. If not, then there is some probability. There is some probability with which it can go to that neighbor. And then again it creates its neighborhood and do the same thing in this new neighborhood. And if it rejects this neighbor, then it will randomly pick one more neighbor from x1. And then it will again do कि अगर it is better, then move to it. and generate its neighbor, and if it is not, then there is some probability with which it will move to that neighbor. When it moves to that neighbor, then it creates its neighborhood and repeats the process again. If you use this graph, then it will be better.
It means, no, so this means you are thinking that from this neighborhood, it may happen that none of the neighbors are better than x1, but already some probability has been mapped. So that probability, which will be having highest probability, will be considered as the next seed.
No, no, not high. It is doing one at a time. It is doing one at a time, huh? So when it is not doing exhaustive search. जिसमें भी it gives the probability कि move करो, it will move. It will not do exhaustive search. Like local search was exhausting the neighborhood search. This simulated annealing is doing one at a time. If it gives a probability कि move to it, then it will not do that all neighborhood. It will just move to that new neighbor.
Let's say then, say x13 has been picked up, and which is not a good solution, has given a probability of say 0.5.
Okay.
Then what will happen?
So it will. So how does it picks? अगर आप ये पूछ रहे हैं, so you see, suppose this value e to the power minus delta e by t for this x3 is equals to 0.5, right? So what it will do is it will do a random number generator, and it will see कि random number 0 कितना आया है. Suppose it came 0.3. So this 0.3 is less than 0.5, so it will not pick x13. Suppose that random number generator gave 0.8. So the this is more than 0.5, so it will say okay, go to x13. This is how you do it in a computer. So suppose the probability is coming 0.5. Now how do we know कि इसमें जाना है कि नहीं जाना है? So this is the probability. You generate a random number between 0 and 1. If that random number, the value of that random number is less than that probability, you don't move that to that neighbor. If that random number value is more than this probability, then you move to that neighbor. This is how we do this in computer. All right.
Okay, can you go to that algorithm, that slide? Yeah. Here where that probability, the acceptance is dash with probability certain value.
So
then
this
next iteration is started, and then how that will be again.
So
that probability will be used.
So when I write except s dashed with probability this, everything हो रहा है वहाँ पे. So it is obtaining the probability of this. It is generating a random number. If that value is more than the probability, it accepts s dashed. If that random number is less than the probability, it rejects s dashed.
Okay. Okay.
So this line is a compound line. This is a written very shortly, but it is compound line. First you have to obtain the probability, then you have to generate a random number and see if that is having a more value than the probability. If it is so, then we accept s dashed, otherwise we reject s dashed.
Okay.
Any more doubt? We have exceeded the time, I see. Okay, so one error I have over here is it should be e to the power minus delta e by t. I will correct it. And over here also in this table I had given -1, -2, -3 should have been 1, 2 and 3. But in the algorithm I have written it correctly. Okay, so just be cautious. I will correct that in the other slide which I'll upload. I cannot correct it here. So yeah, be careful when you read this.
But what the delta E, the way you are defining, that equation also may be true for maximization problem. This is the minimization problem, then delta E may e to the power minus delta E by t.
Yes,
if it is maximization problem, it can be positive also, I think. I don't.
This is a minimization problem. For a maximization problem, it should be the other way. So this algorithm for a minimization problem.
Yeah. No, in that expression you are saying that is the expression is wrong. If we consider that expression from the maximization problem, that expression is correct again.
Correct. Yes. Yes, correct. Okay, so thank you. Thank you for joining. I'll end the meeting here.